Have you ever thought about how electrical wiring stays organized behind the walls of your house? If every wire just ran in a straight line, they would cross and tangle, making maintenance difficult and increasing the risk of electrical issues. But electricians use careful planning and an interesting mathematical concept called book-embedded graph theory to keep everything structured and efficient. Book-embedded graph theory is a branch of graph theory that studies how graphs can be drawn in a book embedding, which consists of a spine, a straight line, and a set of pages, half a planes extending from the spine, like the pages of an open book. The goal is to place the vertices along the spine and draw the edges within pages, while minimizing page crossings and the number of pages required. Imagine designing the electrical wiring for a house with the following rooms: a main power source, the central power source supplying electricity to all rooms. A living room needs connections for lighting, appliances, and outlets. Kitchen requires power for cooking appliances, refrigerators, and lighting. B1 and B2 bedrooms 1 and 2 need outlets, lighting, and possibly air conditioning. If we were to connect every room to every other room in the most straightforward way, we'd get a complete graph, which looks like a tangled mess of wires. This isn't practical because too many wires will overlap, making installation complex. More materials, wires, conduits are required, increasing cost. Troubleshooting and maintenance become difficult. The house wiring system can be represented as an undirected graph equals G equals 5, where vertices V represent electrical nodes, rooms, and main power source, edges E represent electrical connections, wires. The complete graph before optimization is K5, meaning every node connects to every other node. This leads to 10 edges, which results in multiple intersections if directly implemented. Now, let's transform this into a book-embedded graph. First, define the layers pages. The main power source and distributes electricity to key points like the kitchen K, living room L, and bedrooms B1 and B2. The first page has M connected to B2 while L is connected to B1 and B2. The second page has M connected to both K and B1. The last page has K connected to B2. Since wiring every room directly would create too many crossings, we embed the graph into 3 pages, each forming a planar subgraph. This works mathematically because point 1. Each page is a planar graph, meaning no edges cross within that layer. 2. The graph's book thickness is 3, meaning it can be embedded in a book with 3 pages while avoiding crossings. 3. This structure optimizes wiring, reducing unnecessary overlaps and making installation more efficient.